Hello, Science Nines. Welcome today. I want to spend a minute on how electricity is analogous to water, and I also want to talk about something called schematics today. And it'll just build into the notes that you already have. I have here a nice, I guess, summary of voltage, current, and resistance. And in class, we would kind of go through all of these, but I want you to be familiar with primarily the waterfall analogy and the hose analogy out of this diagram. And as well, it doesn't hurt you to see the Ohm's law formulas, which you've kind of already been using, which is awesome. I've been seeing that a number of you are getting those, or you're understanding those. What we need to know about electricity is that it acts a lot like water. And when we think of a river of water, or even a waterfall, I got a picture of that here. The idea is that voltage is analogous to the height of the waterfall. And what that really means is if you consider how high the waterfall, or say the height of the waterfall from say there to there, if you're looking at this picture, then the water has high potential energy at the top, and then it loses that energy, or it converts that energy from potential energy into kinetic energy, or the energy of movement. So a waterfall that was only this high would not have as much energy at the bottom, or the water wouldn't have as much energy at the bottom as the higher waterfall. So the idea there is that as it says in this compression, the height of the waterfall is analogous to voltage. Now, with the hose, if you're talking about a garden hose, voltage is the speed or the pressure. So the higher energy water will happen if you have a narrow hose, or if you take your thumb and you put it over a garden hose. You guys have all done that in the summertime. You can change the speed or the pressure. So those are two really good analogies that might help you understand what voltage is, because just like in those examples for water, electricity is identical. Current is, again, the easy one. Current is just the analogy is the amount of water flowing in a river is equal or analogous to the amount of current that's flowing in a wire. So, and the names are obviously the same. So hopefully that's not too hard to connect. Fun one to recognize, though, is resistance. And resistance is kind of the new idea that we're learning here. In a river or a waterfall, anything that restricts the flow of water would be comparable to resistance. So I put rocks here as one example. I mean, we could add like a dam, or you could say trees, or anything that's anything that's in the water that's restricting the flow of water. And in a hose analogy, if you think of I like thinking of a fireman's hose. If you've ever seen one, they're huge. They can have quite a large diameter, something like this or whatever. You get a whole bunch of water very easily through that pipe. Or if you have you could contrast that with a really tiny hose, one that you'd be restricted in how much water you could get through a tiny hose. When I say tiny, I mean the diameter. So it's the same thing with electricity. If you have a really thick wire, then more electrical current can get through that wire versus a very thin one. And we touched on that a little bit earlier. So also on this diagram, it does highlight the units, which I kind of ran out of time yesterday. I like looking at this here. This is the symbol for ohms. And this symbol here is the Greek letter omega. Omega is the last letter in the Greek alphabet. And just for fun, the longer you take science or physics, the more Greek letters you will learn, because we use them all the time to identify things. So that's all I wanted to say about that. I want to move into what we call schematics. This is one of the items on the notes. And these are symbols that you need to know. You will see these on the test or on a quiz or on a diagram, and you need to understand what they're telling you. Most of them are pretty straightforward, so I don't think you have too much difficulty with them. I will add a couple highlights to this. As you can see in here, the symbol for a conductor is just a straight line. and we've already seen those. A cell has the long terminal and the negative, or long terminal and short terminal, and you should remember that the long terminal is positive and the short terminal is negative. And that actually applies the same on a battery, because a battery is just more than one cell. You can see that there's two cells in the schematic I'm throwing at you, and you can have as many cells as you need. Moving down, a lamp is, we've already seen that one, just a kind of a squiggly representing the filament with a circle around it for the glass. A resistor, at least in North America, there's other symbols in different countries. And in North America, the symbol for resistor looks like kind of some jagged shark teeth or whatever. And resistors obviously control the flow of electricity. A switch is kind of a fun one. It just looks like this. This is an open switch. If you were to draw a closed switch, it would look something like this, where you would just, you can see that that little gate sort of closes. And when it closes, that means things are on. That means you have a pathway for current to flow. As soon as you open it, there's no current. So that should make sense in some of the other examples we're going to look at. An ammeter, circle with an A, voltmeter with a V. Rheostat, here she is. This is a resistor. You can see the teeth, but then there's a kind of a perpendicular arrow, and that didn't really come out great. It's kind of more like a, like a perpendicular line with an arrow coming down to it. I've seen other versions of that, but most times you'd have a key that would identify different symbols if you needed to know different symbols. A motor, I've seen a motor with like this one here with 3 dots inside a circle. I've also seen a motor with an M inside it, and it's circled like this. So there's a number of different ones. And then there's the last one, there's a fuse. So with, it looks like kind of a half of a wave there in terms of its functionality. So what we're going to get right into right away are 2 different kinds of circuits. And I've got 2 of them here, and these are the names: parallel circuit and series circuit. Right off, we could identify a couple of things on these. If you can find the source. So in this case, in the parallel circuit, here's the source. In the series circuit, here's the source. And we can identify really quick the positive and negative terminal. So this end is the positive terminal because it's the long one, and there's the negative terminal. Here's the negative terminal on this side, and here's the positive. I know they're cells, right? Or sorry, they're batteries. So what that means then is the current will always flow away from the negative terminal and then make its way back to the positive. So on the series circuit, it would go this way, and I guess we could label that if you need, that's current. So with a parallel circuit has multiple pathways, and I guess I could write that. That'll make sense in the other drawings we'll look at in a minute. So what I mean by that is the current can come out of the negative terminal, and it could go through this resistor and then into the positive terminal, or it could go through this one and then all the way, or it could go through this one. Now, what's interesting to note is that the current will always take the most direct path, and so you're not going to get a path like this that goes up through this one and then down through this one and over and like whatever. Okay, I'll just undo that, but that's not going to happen. Electricity will take the most direct path. In a series circuit, there's only one pathway, and you'll see what happens to both current and voltage when there's only one pathway, because there's only one way for the current to go. And as you see in the drawing, they can only do that. Okay, so I'm going to switch now to your notes that had actually had some unfinished portions to it, because I wanted to walk through them with you just briefly here. So in the notes up here, we learned 2 things. In a series circuit, it's the current through each of the components is the same, and the voltage is shared. Now, that may not make a lot of sense just yet, but we are going to look at both of those. In a parallel circuit, it's reversed. In a parallel circuit, it's the voltage across each component that is the same, and it's the current that is shared. Now, that has some advantages in both ways, and we'll look at those right now. Let's come down to the first circuit, and I'm just going to zoom in on it so we can take a look at it. the main thing here is what we're going to say for every one of these cells is we have 3 amps of current available and we have 6 volts of voltage available. That's going to be the same in every one of these cells. When we look at this first one, I think we can pick it up pretty quick that this appears to be a series circuit. There's only one pathway from the negative terminal to the positive. Now, it doesn't really say which one's negative and positive. I guess we could make this one negative and that one positive just for sake of the diagram. What we can say, though, because it's a series circuit, is the volts are shared. So if you look at this carefully, this light bulb only gets 3 volts, and this light bulb only gets 3 volts. So 3 plus 3 would be 6 volts. That's the total voltage. That's what we started with. But note for the current, there's only one path for the current to flow, and each light bulb will get 3 amps of current. Let's go to the one right beneath it. What's different here now, it does appear, I mean, if you can tell, this does appear to be another series circuit because there's only one pathway and the current can only go in one direction. So what's different in this case, though, we still have 3 amps and 6 volts available in the same cell, but now each light bulb only gets 2 volts. Okay, if you remember, volts is an amount of energy per unit of charge. And so if these light bulbs are getting less energy per unit of charge, they will be dimmer. Okay, I'll show you an app, or there's an app that we can play around with these, and I'll post that in the notes later. But these lights are going to be dimmer because they have less energy per unit charge. They still get the same amount of current. That's still the same amount of electrons are making it to each light bulb, but they are dimmer because they have less energy per unit of charge. And again, you can see here that 2 plus 2 plus 2, we still have a total of 6 volts, but there's 3 amps flowing through each light bulb. Let's contrast that, though, with this one. So now if we look at this one, let's identify just again that we still have 3 amps and 6 volts in this cell. And for whatever purpose, I think it's trying to be consistent here, make that negative, this is positive. We have one pathway for the electrons to take, or because they can go through light bulb A, or they can skip A, go through B, and do this, okay, with all those connectors in there. So there's 2 separate pathways. The real advantage of doing this, though, is in a parallel, which is what this is, so there's multiple pathways. In a parallel circuit, the volts are not shared, it's the current this time. So what it means is this light bulb A gets 6 volts and light bulb B gets 6 volts. They both get the same amount of energy per unit charge, which is really cool because it means they are both the same brightness. So I mean, that'll make sense when you look at this animation here, but they're both going to be bright and they'll both be the same brightness. Yes, their current is restricted a little bit, but each electron that's going through, it has that much energy, and that's enough to, at least in this simple drawing, for the light bulbs to have the same brightness, which is kind of cool. So just to expand that a bit further, we come down to look at the last one. Looks like it's a little more complex, but the same pattern occurs. We have 3 amps and 6 volts, and there's negative and positive. But this is another parallel circuit, and what's really clever here is, look at this, each light bulb still gets 6 volts, even though there's 3 of them, because each one has its own pathway to and from the negative to the positive terminal. I'm just having fun here. Obviously, you can see these. And each light bulb will get the same amount of voltage, but yes, each one only gets 1 amp. And if you're following that, all 3 of those add up to 3 amps. But based on our cell source, we also have 6 volts. So what's really neat about these is that all 3 light bulbs will be the same brightness. And as noted in the notes, there's advantages to both of these types of circuits. The majority of the circuits in your home are wired in parallel. And it's obvious if you think through that for a minute, because if one light bulb goes out in your house, all the light bulbs don't go off. Um, each light bulb is on or is usually part of a parallel circuit. And so we tend to use parallel circuits in your homes for almost every one of your circuits. There are some applications where, in an industrial process, you maybe want a series circuit so that if one process fails, the others don't just keep going and keep, stockpiling product or doing something that you don't want to happen. In a lot of cases, you want to be able to shut down the whole circuit. So if one thing fails, then it interrupts the complete pathway and everything else shuts down. Anyway, I hope that's helpful. I'm going to post that and also a bit of some review and quizzes. So take care, you guys.